All right, so this is integration with substitution. It's about the closest thing that we have to the integral of the chain rule, okay? So, this looks like a pretty basic problem, right? Okay, the integral of 20x cubed, and then here we have 5x to the fourth minus 3. The problem is that that's cubed, okay? So we can't, and there is no sort of integral product rule. We can just say the integral of this is the integral of this, and then times the integral of that. Sorry, that would be nice, but there isn't. There is something later on we'll talk about integration by parts, but that doesn't really fit and apply here. Okay? So, well, the way that we've been doing this is we get everything all some like a really long polynomial. Now, don't write this on your paper, but can you imagine doing 5x to the fourth minus 3, and then FOIL that out, 5x to the fourth minus 3. And then let's FOIL it out again, don't write this on your paper again, 5x to the fourth minus 3. So FOIL this out, we'll get a nice 4 terms, maybe we'll condense it to 3. Then we'll multiply it by this guy, right? And we'll get double that number of terms. Then we'll distribute this. You see how this is kind of getting rather large, and then we would take the antiderivative, okay? You might have to do that in some situations, but in these cases we do not. Okay? So what we're going to do is we're going to do what's called a U substitution. We're going to manipulate this integrand here to something that is actually pretty easy to find the integral of. We'll take the integral of that, and then we'll substitute back our values. So it's come up with a helpful alternate term here. We'll call it a U expression. And then take the integral of that simpler version and then convert it back to something like this. So at the beginning, this is going to seem kind of random. I have these set up so these first few kind of all follow the same pattern, so you kind of get a feel for it. All right. One thing that as I look at this and I kind of think about derivatives, I do notice that I've got a 5x to the fourth right here, and over here is a 20x cubed, and I'm like, this isn't really familiar, right? Like, for instance, what would happen if I were to take the derivative of 5x to the fourth? What would I get?
20x cubed.
20x cubed, okay? Let's keep that in mind. So over here, what I'm going to do is, we'll write a list of instructions here in a second, but I'm just going to kind of show you what's going on first. I'm going to find a helpful U. In this case, I'm going to set U equals whatever's inside that parentheses. So U is 5x to the fourth minus 3. So U here is a function of x. And so what that means is initially what I can do is I can start doing some substitution here. Instead of writing 5x to the fourth minus 3 cubed, I can just write U cubed. Now I still have a dx and I still have a 20x cubed, so let's go here and I'll say, let's find the derivative of U with respect to x. And y'all already told me the derivative of 5x to the fourth is 20x cubed. The derivative of minus 3 is just going to be 0. And then what I'll do, strangely enough, is I'm actually going to multiply both sides by dx. So I have du equals 20x cubed dx. Now if you look over here, that happens to be exactly the other pieces of the puzzle. 20x cubed and dx. So I'm going to replace those terms with du based on this substitution. And I've now converted this rather complex, annoying integral statement into something that's kind of friendly. The integral of u cubed. What is the antiderivative of u cubed? Class?
U to the fourth over 4.
U to the fourth over 4 plus c. And now what I do is I go back and substitute in my value for u up here. So I'll say 5x to the fourth minus 3 to the 4th over 4 plus c. And that should be my answer. Go ahead, Roger, what's your question?
Why is du not in the formula?
What's that?
Why is du not in the answer? Times du.
Okay, du is a way of communicating that my variable of integration is u. Okay? Sort of like when we were to say, what's the derivative with respect to x of x squared? The dx was saying, hey, x is the thing that I want you to take the derivative of. Okay? So that's what the du is communicating. It's telling us the variable of integration. Alright? And I can't remember which day you particularly missed, but this was a big one. Okay? We're going and it's not really that huge if you can just get your mind to think backwards. No big deal. We know pop down, power down, pop down the 2, power down the 2 of 1. Okay? Well, this is just pop up, right? So the 3 turns into a 4, and then divide up. Take that number and put it in the divisor. Okay. James, how can we check our work? How can we verify that this right here is the antiderivative of that?
Get the derivative.
Yeah, let's take the derivative of it. So let's go ahead and take the derivative real quickly. So I'll need to apply the chain rule here, right? So pop down the 4. When I do that, we'll see that's cancel out the 4. The inside stays intact, so 5x to the 4th minus 3, power down to the 3, times the derivative of the inside, which is going to be 20x cubed minus 0. And the derivative of plus c
0.
is 0. So those cancel, and I have 20x cubed times the quantity 5x to the 4th minus 3 cubed, which is my integrand right there. So you can kind of see that u substitution is sort of like the anti chain rule. All right. So that's our answer right there. All right. Let's go ahead and look at number 2. Number 2 looks really a lot alike. Let's go down to number. Okay, let's go to number 5. If we're going to write some steps down, step number 1 is going to be find a useful u. Are you kidding me? We got another 5x to the 4th right there. There. I take it back. We're doing number 6. Alright, number 6 here, we have 4x to the 4th plus 3 quantity to the negative 5th times 16x cubed. Once again, when we look at this, at this point there is no way that we could do this the long way. Ivan, you missed our fun discussion. Can you imagine 16x cubed divided by, this is 4x to the 4th plus 3 to the 5th. That's really what this is. We have no way of doing it with the dx, obviously. We have no way of handling this. We could try to multiply all this out to the 5th, which would be disgusting, but we could do it. Even then, we would have to figure out what this, how to do this polynomial divided by that polynomial, which this one's larger, so really wouldn't help us out. We still end up with a remainder term. Yeah, this is good. This is we're sort of out of luck on this one. Except for the fact that u substitution comes to our rescue. So I notice once again that the derivative of the inside here, 4x to the 4th plus 3, if I take the derivative of that, I'm going to get 16x cubed. So our useful u in this case is whatever's inside that parentheses. So 4x to the 4th plus 3. So that becomes u to the negative 5th. Step number 2 is going to be find du over dx. So take the derivative of u with respect to x. So 16x cubed. Step number 3. Solve for du. So multiply both sides by dx, we have du equals 16x cubed dx, which happens to be exactly the other piece of the puzzle, so du. And now we take the antiderivative. James, antiderivative u to the negative 5.
U to the negative 4 over negative 4.
I agree. Keep going.
Plus c.
Plus c. Alright. So I'm going to put this, I'm going to do two things at once. I'm going to put that u in the denominator, so this becomes negative 4, and I would write u to the 4th right here, but why bother when I can at the same time substitute in what u happens to be. So 4x to the 4th plus 3 to the 4th plus c. If you want to verify your work, once again, you can take the derivative of that and see if it equals the integral. Any questions? All right, let's go to the back page. Maybe it's gonna get harder. I don't know. Number 7 doesn't look too bad. All right, let's go ahead and apply our process here. Somebody tell me, what do you think would be a useful u in this situation?
X squared plus 3.
X squared plus 3. Next up, du over dx. Du over dx equals, call it out to me here.
2x.
Then solve for du. So du equals 2x dx. Something's not right here. Oh. We've done everything right. But this one isn't simplifying like the other one did. Okay, I've got this right here. X squared plus 3, I can write that as u to the negative 4th. But here I have 10x dx. That's not an exact match for my du. I have 2x dx. What do you suggest?
Multiply by 5.
Multiply by 5. So I'm going to take this down here and multiply it by 5. Multiply that by 5. So I have 5 du equals 10x dx. Okay. So now I can, instead of writing 10x dx, I'm going to write times 5 du. So maybe I should add another step here. Step number 4, multiply as needed to obtain a proper term to substitute into the problem. Because we need everything to be accounted for. We need to convert absolutely every single one of those terms as needed. So I'm going to rewrite this just, we know the constant multiple rule, where if you have a function times a constant inside the integrand, we can pull that constant out and just have this as integral of u to the 5th, sorry, integral of u to the negative fourth du. And now we're off to the races. So 5, Harley, help me out here, antiderivative of u to the negative fourth.
Oh, I was gonna ask if it was gonna be the, never mind, you didn't mess that. It's gonna be negative 3 over negative.
Yep. Keep going.
Or plus c.
Yeah, plus c. And then, so you're expert at this now, Harley. Remember, anything to the negative exponent
You're gonna put in the 5.
for the denominator. So actually, I'm gonna, and this negative, which happens to be a multiplier, I'm gonna stick that out in the front. So I have negative 5 in the numerator, 3 in the denominator, and then instead of writing u to the third down there, I'm gonna say x squared plus 3 to the third in the denominator plus c. So for those of you that end up using calculus in later applications and things like that, this is a technique for solving hard to solve integrals, okay? You can imagine, what if this happened to be like 10x squared, right? Would this work? Maybe, I mean, not exactly. I mean, the whole reason why that 10x cancels is because it's the derivative of this term inside here, okay? So maybe it would work, maybe it wouldn't, okay? We're not exactly, I mean, it wouldn't work exactly the same because you wouldn't be able to cancel out the derivative. There might be other mechanisms and other substitutions that we could make, okay? But just to kind of give you the overall big picture, integrals are a nasty business, okay? They're not like derivatives where you literally just turn the crank and do the same thing every single time. Integrals, and you can handle lots of different things. I mean, it doesn't matter what your function looks like. If it's a function over another function, you just do the quotient rule, and it's going to work every single time. No matter if you can find the derivative of the numerator and the derivative of the denominator, then you can do derivative of the denominator times derivative of the numerator minus derivative of the numerator. You can do all of that stuff. You can't, there's no sort of like magic quotient rule or like the chain rule. It doesn't matter what is inside the other thing. You just take the derivative of the outside, keep the inside intact, times the derivative of the inside. Okay? You can't do that with integrals. You kind of have like to try just the direct way that we did it, like just try something like this. But if what you're looking at, your integrand, isn't that, you've got to do a substitution. Later on, we'll find sometimes this gets kind of annoying and frustrating. You have to go to a table where there's like a table of integrals. Sometimes you just have to do an approximation, stuff like that. So there's integrals are ugly, and so what we've done is in this particular situation, they have found exact problems that fit this pattern, this U substitution pattern, and those are the ones that we're doing for homework. We'll kind of get locked in on those, but it's the kind of thing where in the real world, you're not sure, you're just going to be given a situation which is modeled off of some real life scenario, and you're going to have to, find the integral for whatever reasons, and part of the challenge at that point is deciding which one of those techniques is going to help you solve, get that value. Okay? So,
I have a question.
Sure.
How'd you get 2x from d over dx? I thought it was supposed to. What I thought was.
Okay, so I have this function right up here, u equals x squared,
Yeah,
right?
That's
Okay. All right. Just imagine this is this. F of x equals x squared plus 3. Let's take the derivative. F prime equals 2x. So instead of f of x, I have u.
Oh, we just find the derivative of u. And
Yep.
That's what dv over d. Oh, god.
This is not a v. This is supposed to be a u.
Yeah.
It does kind of look like a v. But yeah, du over dx. All right, let's scan through the rest of these. Are there any more on that page that look kind of intimidating? Why don't you all do that one? See if you can do number 12 as a table. When you get 12, do 14. If you get it right, then I'll give you the homework. James, go ahead and stop the video if you don't mind.